Good morning everyone. I am Fatimatul Hiba M from First MCA. Today I am presenting a seminar on the topic threads. Threads are essential part of modern operating system and understanding them help us build efficient and responsive applications. What is thread? A thread is the smallest unit of execution handled by the CPU. It is also called lightweight process because it exists inside a process and shares the same code, data and memory. Because multiple threads share resources and they help improve responsiveness, CPU utilization, parallel execution, faster communication. This is why almost every modern application uses threads. Process versus threads. Here you can see the difference between a process and a thread. This is a diagram of process and a thread. The diagram illustrates relationship between a process, multiple thread within the process, their individual stacks and operating system kernel. Process is shown as a large blue oval representing an executing program that serves as a container for the thread. Thread T1, T2, T3 are multiple threads existing in a single process. A process has its own PCB, process control block, and its own memory space. A thread has only a small TCB, thread control block, and shares the memory of its parent process. The diagram illustrates the concept. The key components typically found within a PCB and TCB, which are crucial data structure used by the operating system for managing processes and threads. A PCB contains pointer, process state, process number, PC, program counter, register, memory limits, list of open files. While thread control block contains thread ID, thread state, program counter, register, stack pointer, priority, thread specific data and pointer to PCB. Types of threads. There are major three types of threads. One user level threads, two kernel level threads and three hybrid threads. User level thread managed in user space, fast to create and switch, but if one thread blocks, the whole process get blocked. Kernel level threads managed by the OS kernel, slower to create, but they allow true parallelism on multi-core processors. Hybrid threads, a combination of both models. User thread get mapped onto fewer kernel threads, balancing speed and parallelism. The diagram here shows multiple user level threads being mapped to fewer kernel level threads. The OS schedules only the kernel threads while user threads are managed by a library. This gives the speed of user threads and parallelism of kernel threads. Multi-core processing. Modern CPUs have multiple cores. Each core can run one or more threads. Multi-core processing gives us real parallelism, higher throughput, energy efficiency, faster execution for multi-threaded programs. Operating systems that support SMP can schedule threads across all available cores. The diagram illustrates the concept of parallel execution on a multi-core system, where multiple tasks can run simultaneously on different processor cores. Multi-core system. The system has two separate processor cores labeled core 1 and core 2. Each core is a physical CPU capable of running its own thread independently. The diagram shows four distinct threads T1, T2, T3 and T4 being executed simultaneous execution. At this moment, two threads are running in parallel, T1 and T2, T3 and T4, etc. What is multi-threading? Multi-threading means executing multiple threads concurrently within the same process. This helps to reduce CPU IDE time, increases performance and improves responsiveness. Tasks that slow when done sequentially become faster using multiple threads. Single versus multiple threads. In this diagram, single thread process handles tasks one after another. The multi-threaded process divides work among multiple threads. This reduces waiting time and improves overall application performance. Multi-threaded server architecture. A client sends a request to the server and the server immediately creates a new dedicated thread to handle that specific request. The server then resumes listening for additional client requests without blocking. Each request is serviced by its own thread, allowing the server to remain responsive and processes multiple clients simultaneously. Types of multi-threading. We have three models here: many to one, one to one, many to many. Many to one. Many user threads map to one kernel thread. Cheap but blocks easily. This is the figure of many to one. And next one is one to one. Each user thread has its own kernel thread. Supports parallelism and but expensive. This is one to one. And this many to many. User threads share several kernel threads, balanced and efficient. This is many to many diagram. These diagrams show how threads are mapped to kernel threads in each model. Multi-threading versus multiprocessing. Multi-threading uses shared memory within one process. Multiprocessing uses separate process with separate memory. Thread communicate faster, but problems like race condition can affect the whole process. This is the combined concept of multi-core and multi-threading. The application of threads. Threads are used in web servers, OS background tasks, multimedia application, gaming and real-time systems. The advantages of threads are faster context switching, high responsiveness, good for multi-core processors, scalability. The disadvantages are race conditions, synchronization problem, deadlocks, debugging complexity. A bug in one thread may crash the entire process. To conclude, thread plays a major role in achieving parallelism and performance in modern system. Understanding processes, threads, their model and multi-core execution helps us write efficient and scalable programs.